Did you know that scientists use giant squid to study nerve cells? Giant squid have been long favorites with neuroscientists because their axons are so big you can see it with the naked eye. The bigger the axon, the easier it is to visually comprehend how electrochemical communication works. Resting membrane potential. When a cell is at rest, it means that the electrolytes are unequally distributed between the extracellular fluid on the outside of the plasma membrane and the intracellular fluid inside the membrane walls. Although the concentrations of the different ions attempt to balance out, during the resting state, the membrane potential is only permeable to the potassium ions. So while potassium ions are heading out of the intracellular fluid by diffusion, the various sizes and charges of anions, such as organic acids, proteins, ATP, and RNA, are still trapped inside. The more potassium that leaves, the more negatively charged the intracellular fluid becomes, which results in the fluid becoming so negatively charged, it reverts some of those escaped potassium ions back down its concentration gradient by its negative attraction. However, the intracellular fluid's negative attraction is short-lived because as soon as more potassium enters its positive charge, it decreases the fluid's negative strength. Unable to attract back enough of the needed positive charge, the membrane sodium channels slightly open. Although the energy needed for the sodium ions to pass into the intracellular fluid will cost 3 potassium ions in order to receive 2 of the sodium ions. Eventually, this trickle trade effect passes enough sodium ions for the intracellular fluid and the extracellular fluid to be satisfied, leaving the resting potential intracellular voltage at negative 70 millivolts, where the intracellular voltage is negatively charged and the extracellular fluid has a positive charge. Even though a neuron is said to be at rest because it is not producing signals, it is highly active, maintaining its resting membrane potential. And action potentials both start off when a stimulation has to happen, like a minor exposure to light, to heat, or physical bump, for example. The change is sensed, and the dendrites send a notification signal. As the signal makes its way through the dendrites, it enters the soma, where the signal needs to pass through the soma's gated channels to the axon hillock for a physical reaction to be triggered. But in most cases, with most signals, the soma's channels can handle the situation. When the stimulus signal arrives, the soma's cell membrane channel open, allowing sodium to enter the intracellular fluid. The local areas of that open channel become depolarized, and local potential is produced. Local potential can vary depending on the strength of the signal, so as more sodium enters that particular area of the cell, the gated channels that never opened remain closed to maintain the resting potential of negative 70 millivolts. This makes it easier for the cell membrane, once stimulation has ceased, to reverse the effects and return back to resting potential. As the signal passes through each cell in the soma, the same effect happens, causing the signal to become weaker and weaker and causing the gated channels of the cell membrane to be fewer and fewer as the signal passes from cell to cell, until at last the signal has been diffused and the cells can easily reverse their membrane voltage back to resting position. While the soma has only about 50 to 70 gated channels per micrometer and cannot generate action potential, the trigger zone, mentioned earlier, has 300 to 500 channels and the potential to produce action. So, if the stimulated signal was strong enough to not be diffused by local potential in the soma cell membrane, it would eventually reach axon hillock and possibly trigger an action potential. For action potential to be activated, the same actions of local potential first start by opening selective gate channels that allow sodium ions to enter the intercellular fluid. Now, if the signal is not strong enough, the intercellular fluid does not exceed negative 55 millivolts. The cell membrane will handle the signal as if it would as local potential, diffuse the signal, and revert back to resting potential. However, if the signal is strong enough and continues to depolarize the intercellular fluid, eventually it will reach a critical voltage known as the threshold. An irreversible charge of around negative 55 millivolt will trigger the voltage charged channels to quickly open, resulting in a downpour of sodium ions, and even slowly open the potassium channel, allowing potassium ions to trickle in as well. With sodium flooding the intracellular fluid and potassium adding its flare, they create a positive feedback loop that makes the membrane voltage rise rapidly to a critical voltage. Once the neuron's threshold is met, the neuron then fires its maximum positive voltage. Unlike local potential, where the signal gets weaker as it travels, action potential signals are non-detrimental, which means that the signal does not get shorter or weaker as it passes down the axon until reaching its final destination, the synaptic knobs. As soon as the intracellular fluid reaches 0 millivolt, the sodium gates immediately close, even though by this time the potassium gates are fully open. However, once the ICF exceed 0 millivolts and the ICF have a positive charge, it then repels the potassium ions back through the channel into the ECF. When the intracellular fluid has a positive charge and the extracellular fluid has a negative charge, this is known as hyperdepolarization, the complete opposite of the resting potential.